Have you ever looked at a perfectly crafted project schedule? You know, the ones with that crisp mathematical certainty, and just wondered why the actual software project still completely missed its deadline? Yeah, you are definitely not alone. It's the classic illusion of Gantt charts. They look absolutely gorgeous, completely foolproof on a manager's monitor, right? But then they fail spectacularly in the trenches. Well, welcome to this explainer. Today, we're going to unpack exactly why perfectly planned projects fall apart and how modern management theories are trying to fix them. We're diving right into that fascinating, messy friction between mathematical ideals and actual human reality.
Here's our roadmap for today. 1. Mapping the perfect project. 2. Finding the critical path. 3. The human constraint twist. 4. Leveling the project schedule. And finally, number 5. Rethinking estimating safety.
Section 1. Mapping the perfect project. Okay, let's dive into this by looking at some specific, tangible project data from our source material. All right, take a look at this raw task data. We've got 5 specific tasks required to actually build our software. Notice how they're logically divided up? We have our A branch tasks, requirements, back-end coding, and QA testing, and those run in a strict sequence, one after the other. Then we have our B branch, which is UI development, just sitting on its own. And this kind of logical division really matters in real-world software development. Splitting into A and B branches is super typical when, say, front-end and back-end teams are working simultaneously to try and speed the whole thing up. Finally, there's integration. That's the grand finale, tying both of those branches together. So, when we visualize that raw data, we get this living network diagram. You can clearly see branch A progressing right across the top, going from requirements to back-end and over to QA. Meanwhile, branch B, UI development, runs parallel right along the bottom. But the absolute crucial point here is that final integration task, B2. It literally cannot even begin until both back-end coding and UI development are 100% finished.
Section 2. Finding the critical path. So, now that we have our map, our very first goal is to calculate the mathematical ideal. Basically, if everything goes exactly according to plan, how fast can this project be completed?
To figure this out, we run what's called a forward pass. It's a pretty beautiful concept in theory, honestly. We essentially trace the longest path through our network, adding up all those task durations starting from day 0. We're finding out exactly when we theoretically cross the finish line. We just calculate the earliest possible start and finish times for every single task, systematically mapping out the whole timeline until we hit that ultimate completion date. And when we crunch those numbers on our project, we hit our magic mathematical ideal, 38 days. Since the QA testing task is the final step in the longest branch, its completion on day 38 dictates the entire project's finish line. So in a perfect world, boom, there's our project deadline. And wow, this number is powerful. Once it's calculated, stakeholders have a nasty habit of etching it in stone, right? It creates this rigid, formal expectation across the entire company before reality even has a chance to hit. But, as you and I both know, projects rarely run perfectly. That's exactly where the backward pass comes in, which helps us calculate something called float. Now, float isn't just some dry math term. Think of it as the everyday breathing room built directly into your schedule. It tells us exactly how much a specific task can be delayed or extended before it actually pushes back that rigid 38-day final deadline. And here is a super fascinating takeaway from our data. The UI development task has a massive 18 days of float. Seriously, if you've ever managed a project, you know that 18 days of float feels like an absolute luxury. Mathematically, it guarantees that UI won't be your bottleneck. Or, well, so the theory goes. Your UI team could theoretically sit on their hands, start their 12-day task nearly 3 weeks late, and the overall 38-day project deadline would still be perfectly safe. Crazy, right?
Section 3. The human constraint twist. Okay, so mathematically, our project is totally flawless. We know the deadline, we know exactly where we have breathing room. But there is a massive, glaring flaw in traditional critical path scheduling. These mathematical models, they assume you have infinite resources at your disposal. Which brings us to a really pivotal question for you. What actually happens when this pristine, perfect academic exercise crashes headfirst into a messy, relatable, real-world workplace? Now, what's really interesting about this slide is what happens when we introduce the actual humans doing the work. Suddenly, a completely hidden scheduling conflict emerges in our resource column. Our poor, overcaffeinated senior developer, let's just call him Dave, is double booked. Actually, scratch that. He's triple booked. He's assigned to back-end coding, UI development, and integration.
We literally have one person assigned to 3 separate tasks. And here is exactly where the math breaks down. According to our perfect 38-day schedule, back-end coding runs from day 8 to day 28. But UI development runs from day 0 to day 12. So unless Dave has somehow figured out human cloning over the weekend, this perfect 38-day schedule is physically impossible. He's required to be in 2 places at once between days 8 and 12, frantically trying to write back-end logic and UI code at the exact same time. No way.
Section 4. Leveling the project schedule. Well, since we can't clone our developer, we have to fix this clash. And we do this through a process called resource leveling, which basically forces these overlapping tasks into a strict, workable sequence.
Because Dave can only do one thing at a time, we really have to weigh the trade-offs of the 2 feasible realities we're left with. Ordering 1. We tell Dave to do the back-end coding first. But because that delays the UI work so drastically, our total project duration blows up from 38 days to a massive 48 days. Ouch. Then there's ordering 2. We have Dave tackle the shorter UI development first. This is slightly better, but it still pushes our final project duration out to 42 days.
Naturally, we go with the lesser of 2 evils. So 42 days is now our newly adopted, realistic baseline. I mean, let that sink in for a second. This is a 4-day penalty incurred before a single line of code is even written. It totally proves why so many projects feel like they're behind schedule on day 1. Simply put, the initial unconstrained plan completely ignored the basic reality of our human resources.
Section 5. Rethinking estimating safety. This kind of penalty forces us to elevate our thinking. If scheduling math is so easily broken by reality, how might we overhaul this entire flawed system? This is where we move from traditional scheduling mechanics to a much more radical management strategy.
Just think about how we traditionally estimate. Every single time a developer gives an estimate for a task, they bake in a hidden safety margin to protect themselves, right? It's human nature. Nobody wants to be the one missing a deadline. But when tasks are scheduled back-to-back, all those hidden individual safety margins accumulate and artificially inflate the entire schedule. Add in our resource constraints, which, remember, already bumped us up to 42 days, and you have a horribly bloated project timeline right out of the gate. Well, the critical chain method, or CCPM, proposes a totally radical alternative. It completely strips away all those embedded safety margins from the individual tasks. Instead, it pools all that rescued time together and creates one single, transparent, shared project buffer at the very end of the schedule. That means if one task goes a little long, it just eats into the shared buffer, not the final deadline. This keeps the whole team laser-focused on the actual finish line rather than hiding behind their own individual task padding.
And all of this leaves us with a really provocative thought. In an industry literally defined by hidden padding and missed deadlines, could stripping away your team's individual safety nets actually be the secret key to delivering on time? Can one single shared buffer really save a project from disaster? It's a massively compelling shift in how we manage humans, trust, and time, and honestly, it's definitely something you might want to challenge your team with on your next major project.